We're going to talk about considerations in cross-platform cryptography, which, sounds really scary, I'm sure. I'm curious, how many people in here would consider themselves like experts in cryptography? Okay, that's good. That's what I thought, honestly. Because I'm not an expert at cryptography. I'm just an app maker. I assume like everyone here, I'm just an app maker. And as an app maker, I just kind of have to become an expert with whatever framework I have to work with as I have to work with it as the job requires. And it just so happens that I've worked with cryptography recently, specifically moving stuff between the platforms, and found just some interesting gotchas, unexpected types of things that I thought would be good to collect and share for this conference because of its focus on cross-platform. But at the same time, I don't know if any of you have recently worked with cryptography or if it's been a long time or whatever, but I thought it would be good for us to just sort of get all on the same page by just having sort of a brief, possibly reintroduction to elliptic curve cryptography. And if you don't know what any of those words mean, we'll get to most of them. So I'm gonna sort of just talk about cryptography in general for a while, and then I'm gonna tell sort of these these stories, these cross-platform things that I noticed. And then I'm going to have, if I have time left, I'm going to have just sort of like some feels time and talk about some things that are not really related to cryptography at all. So if you're not into that, don't worry, you'll see the warning and then you can just leave. You're just here for the math, you're not here for the feels. It's 100% okay, you'll know. But first we'll get into some good hard stuff so that you feel like you learned something today. Okay, so a brief reintroduction to elliptic curve cryptography. I needed to get into the zone for this, right? Because cryptography has a reputation for being somewhat hardcore, and it also has a reputation for being super, super, super nerdy. So I had to find something that is both super hardcore and super nerdy. So I just put on some really hardcore nerdy gangster rap. I put on some MC++, really hardcore stuff. I love MC++, actually. He has the best name of anybody in hip-hop. But I even better like his rival, who records diss tracks about this guy. Because it's hip-hop, right? So people gotta hate. And he has the best lyric of any hip-hop song of all time, as far as I'm concerned. I offer them a spliff from off my hash table. Yeah. So, if you're visiting Amsterdam, wink, wink, nudge, nudge. And if you're from here in the Netherlands, then, eye roll. But I thought that'd be a funny way to get into hashing. And I thought that it's good to sort of make sure we all understand what hashing is, because hashing is at the core of really all cryptography. Hashing is, when we talk about hashing, we're talking about a hash function. And a hash function is basically a function that is going to take some input value and produce some output value with some sort of magical hashy properties. We can represent this mathematically with this sort of f of x equals y. You might remember this from algebra, where you have a function f that takes an input x and returns an output y. Or we could represent this in code as a function called hash, which has a parameter of input and a return of output with some implementation detail inside. Or you can represent it as a big blue box with an input funnel and an output funnel and magic sparkles that operate on colorful shapes. Computers are worlds of metaphors. These are all the same. And so with the hashing function, what we're doing is we're taking some input, which we call a message, and we're turning it into some output, which we call a digest. And not always, but almost always, the digest is going to be something that is completely unrecognizable from the message. You cannot look at the digest and know what the message was. It looks just like a bunch of random ones and zeros. If, on the other hand, you give the hashing function some different input, then it's going to produce some different, apparently random blob of ones and zeros, right? And so what we have basically is something that is simultaneously sort of anonymizing in its behavior, but at the same time something that maintains a sort of unique identity, right? So we can say that even if we don't know what two objects are, if they have the same hash, then they are the same. So what happens if you put the same thing into a hashing algorithm more than once? Do you get the same apparently random thing out, or do you get some other apparently random thing out? And that, of course, really depends on the actual implementation, on the hashing algorithm. Some of them are deterministic, and some of them are random. So one example of a hashing algorithm that we see all the time is the so-called secure hashing algorithm. A very common flavor of this is SHA-256, which is the secure hashing algorithm in a 256-bit implementation, which basically means that if you give it any pile of ones and zeros, it will produce an apparently random deterministic pile of exactly 256 ones and zeros. That's what SHA-256 does. So what? What's the big deal about this? This very simple transformation of one blob of ones and zeros to another blob of ones and zeros has just all kinds of astounding consequences that aren't necessarily obvious from the simplicity of the math. For example, the aforementioned hash table, right? Like, okay, if I was looking for somebody in this theater, and I just had the person's name, and I didn't want to just announce it to everybody at the same time, and I had to sort of like go to every single person in the theater and ask them if they were the person I was looking for. I would have to ask somewhere between one and every person in the theater if they were the person I was looking for, right? And when we talk about algorithms, we call that a linear efficiency, right? You may know. But if, on the other hand, I had a system whereby I could take your name and I could hash your name into a seat number, then I would always know exactly where you are. I would say, who are you looking for? This person, hash that, here's where they are, boom. And so it wouldn't matter if we're in the small theater or the big theater, the number of checks I would have to do to find you would be 1 all the time. That's what we call a constant time operation, obviously much, much, much more efficient. That's what a hash table is. A hash table is a big array that has between 0 and n, where n is the maximum size of the number that you get when you hash two things, which will produce two apparently unique numbers. Powerful, interesting stuff, and the basis on which, like a humble Lego brick, everything is built. So another thing you can do with sort of a hashing algorithm is to create something that's called a key pair, right? And a key pair is, well, it's kind of exactly what it sounds like. You have a lock, but instead of there being one key, there's a pair of keys. And the way that these work is that if you lock the lock with the one key, then that lock can only be unlocked by the other key, and vice versa. So if you can use a key to unlock the lock, then you know that it was locked with the other key. And so if I keep one of the keys for myself and make the other key publicly available, I have a way of basically taking something, putting it in a box, locking it with my individual private key, and then anybody out there with the public key can open the box and have the thing in the box and know that I put it there because it had to have been locked with my key because it was unlocked with the other key. That's what a key pair does. So now for what I think is the big exciting thing in all of this, which is elliptic curves. And I say that not because I'm a huge algebra nerd, I'm most definitely not, but because when I say, yeah, I'm working with cryptography, I feel like that makes me sound like a pretty decent nerd. But when I say I'm working with elliptic curve cryptography, people are like, damn, that's some top-level nerding right there. Curves, yeah, wow. So then it's like, what's an elliptic curve? And it's like, well, it's a curve which forms an ellipse. No, I mean, obviously, an elliptic curve is a curve that is a graph of the solutions to the equation y squared equals x cubed plus ax plus b, obviously. One specific curve gets everybody excited, though, and that's y squared equals x cubed plus 7, where a is 0 and b is 7. Because, hey, look at it. I mean, wouldn't you get excited by this curve? You would be surprised how excited people get about this curve. So what can we do with this little piece of math? Well, so here's what we're doing when we're creating a private key. We're taking a piece of memory, and we're putting into that memory a random number, right? We're coming up with a password. Like, this is how crypto works, right? Like, you come up with a password for something. Generating a private key is just coming up with a password, but you're trying to come up with the most secure possible password, which is a long, random password. And then, of course, the weak point in any password is that people know the password, and so we don't want anyone to know the password. We don't ourselves want to know the password. This thing is so secret that it's in a special box, in a special processor, in a separate computer that lives inside the computer. Right? The so-called secure enclave, or the whatever Android calls it, which is like, that is the forefront of mobile security, right? Is this separate secure processor that can do private key operations and hold passwords that are so secure nobody even knows what they are. So we have this secure piece of memory here, and we generate a random number. And you will often hear that random number generators are very important to cryptography, and this is 100% true, because if you have a way of getting into my random number generating process, either of predicting the number or of determining what the number will be when I generate it, you know my password, right? Like, this is how every card trick works, where they're putting the cards down and they know when you're going to say stop. They're forcing the card, and somebody could easily trick you in the same way. Just a few years ago, there was a problem with the random number generator on Android, which caused Android Bitcoin to basically, lose a lot of people their money. So anyway, random number, you generate a random number, and then sparkly magic, and then that will produce a point on this curve. And that point will be, in this case, x, y coordinates that are also big, giant, random-looking numbers. So basically, you're taking one 256-bit number, which, for ease of sanity, is a 32-byte number, and then you're using that to get a coordinate that is x and y, both giant 32-byte numbers. 32-byte number, just for all intents and purposes, is just a really freaking huge number, right? Like, that's two of them. Those are really big numbers. That's kind of like, that's how it works. Like, the numbers are so big that there's no guessing. So that's kind of how this works. And then because the curve has this particular shape where for every x coordinate there's only two possible y coordinates, which are exactly the same except for one being positive and one being negative, you can actually just cut half of this off and just keep the x coordinate itself. And then all you need to remember is whether the y coordinate was positive or negative. And so then you can basically create a public key that is 33 bytes to go with your 32-byte random number private key. So that's sort of what elliptic curves have to do with encryption. So that's the introduction to cryptography. Now you know everything that you need to know to at least hopefully understand the next part. So I think of these as kind of like cross-platform travel tips, because I find that, like, traveling between platforms is very much like traveling between countries. There's different cultures, people speak a different language, and you sort of like find yourself in this position of, kind of being a foreigner and trying to like respect people's like native customs, and it's just interesting working in a cross-platform kind of way. It's an educational and humbling experience. But you can definitely run into some certain gotchas. Here are 4. One is that it's really easy to mess up on the details. Like, you never know, especially in another country, you never know when the difference of one letter changes everything. You just don't know. Another thing you have to be careful for are so-called false friends. And I don't mean like people who scam tourists. I mean two words in two different languages that sound the same but have a different meaning. Right? Like, when I'm speaking Dutch, I always want to say actueel to mean when something is actual. but that's not what that means. It means like current or something. So in other words, like I think I know the word, but actually the word means something different than it does in the language I'm used to. You always have to be careful with conversions, right? Anyone who's ever blown up an appliance by plugging it into another country knows that the easiest way to mess up a conversion is by not realizing that you had to do a conversion. And then, of course, everybody's favorite part of travel is packing and unpacking. So I'll sort of go into these 4 perils as discovered by me. First of all, the details. So if you look at all of the cryptography that is available to you on whatever platform or platforms you're trying to program for, it is a dizzying array of letters and numbers. And even if you know what it all means, it is really difficult to know like where to begin and what to use. And the good news here, and really I think this is maybe the best news when you're trying to do this, is that you have no options whatsoever. If you want to actually make cryptography work between platforms, there's not anything that you're really going to be able to do. And for one very, very simple reason. So what is our goal here? Our goal here is to do cross-platform cryptography. But that's not actually right? That would be like saying that our goal in traveling is to travel. Cross-platform cryptography is like what we suffer through in order to achieve our actual goal, which is to create a great experience, right? That's what we're really trying to do here. And creating a great experience means leaving people alone, right? Letting people do things the normal way. Like letting people, use their native platform the way that their native platform is meant to be used, and to leverage the advantages of that platform, right? So our plan for creating a great experience, I think, always should include leveraging the native platform. And when we're talking about cryptography, leveraging the native platform means using that secure processor architecture that I just went on about as being like the forefront of technology. Like if you are going to do nothing else with your cross-platform crypto, you should at least integrate the mobile secure processors with whatever crypto framework or whatever you're using or building your services on, because this is the good stuff, and this is what people. This is why people have these devices, right? This is why mobile is exciting, because it enables us to do stuff like this and have these native platforms. And if we don't use them, then we're not giving the users their best experience. So what are the details? First of all, the key size, you don't have to worry about it because there's only one for you, and that is 256 bits. Android will also do this in 512, but iOS not yet. So maybe in the future, iOS will support 512, and then you'll have 2 options, or they'll drop 256 and it'll be 512. It's always been 512. But right now it's 256 bits. The algorithm, of course, is going to be elliptic. And because we're going elliptic, we have to decide which curve we're going to use, and the curve is going to be the very memorably named SECP256R1. SECP256R1, obviously very, very popular, has a lot of names, known by a lot of things to a lot of people. Some people call it Prime 256V1 because it's the leader of the Autobots. Some people call it NIST P256. And some people call it SECP256K1. And those people have a lot of really hard to find bugs because these two things are not the same thing at all. 256R1 and 256K1 are very similar but ultimately incompatible curves, which means that your operations will non-deterministically fail increasingly as you get farther from your sort of faulty use of the curve. Which is a very sort of scary, fancy way of saying the hardware cryptography on your phone does not work with Bitcoin. 256K1 is what Bitcoin uses. 256R1 is what the hardware security requires. These two things are incompatible, therefore, these two things are incompatible. For you as an app developer, it means that if you are looking for a crypto framework to use, and you want it to be compatible with the hardware, don't use the Bitcoin library. Even though it's very optimized because it is very old, It is also does not support this stuff, therefore it's not really your best choice. You can use Ethereum, you can use OpenSSL, you can use pretty much anything other than Bitcoin for interfacing with the native hardware. So false friends. False friends are these words where you have two things that are literally the same word, except that the actual meaning is completely different. I ran into this recently when generating a signature. This is the code for both iOS and Android for generating a signature. It's iOS on the top and Android on the bottom. What you're seeing here, even though the way of speaking is different, the parts are the same. You have the key that you're using, you have the input, and then you have the actual hashing algorithm. And the reason why you have this hashing algorithm is because when you create a signature, you're not trying to sort of secretly encrypt the message itself. You're trying to just sort of like authenticate the message by having signed it, so you don't really need all of that complexity. So what you do is you take the thing you're signing, you run it through SHA-256, and then you take that conveniently sized 32-byte hash, and then you sign that. And so you have to tell the signature function which one of these hashes you're going to be using. And that's what the green stuff is. The problem here is that these two things, which say the same thing, have completely different meanings. Because it turns out that when Apple says, create a signature on this hash type, what they mean is, you give me the hash type and I will give you the signature. But when Android says, give me a signature with this hash type, what Android is saying is, give me whatever you want, and I will hash it with this hash type, and then I will sign it. And so in one, you're describing the work you're going to do, and in the other, you're describing the work that you want the function to do. So you can see the problem here is that if you try to run these both the same way, you're going to end up with something double hashed. And so what you end up having to do then is not say you're going to give it this kind of hash, but rather say none, because what you're saying is don't hash this. It's already been hashed. So conversion, anytime you have numbers, you're always going to run into conversion problems, and they're always going to pop up in the most unexpected of places, and you're never going to quite understand why. Here, one conversion problem that I have run into is that Java does not have an unsigned char type. Kotlin has an unsigned char type, but unless you're using native Kotlin, it's going to go through Java eventually, and then it's not going to work. So the long and the short of this is that a lot of times when you're doing crypto stuff, like I said, we're dealing in bytes. And so you want to pass bytes through the Java native interface so that you can interact with some framework that you're using cross-platform. But the problem is that because you don't have an unsigned char, you're going to have signed chars coming through so that you're going to have sort of negative numbers coming in where you're really just expecting a simple bit field. And so what you end up having to do is literally going through the bytes one by one, testing their polarity, and then if they're negative, flipping them. 256 being the size of the char type. We're dealing with bytes, but really, size of. And finally, unpacking. Specifically, unpacking the actual values for your public key and then ultimately for your signature type. There are these sort of interchange formats that you run into such that the data are compatible, but they won't read across platform because the metadata are not compatible. And so it's helpful to sort of have a notion of what these formats look like. And unfortunately, I have to show this in hex. And so if you are not familiar with hex, I'm not going to show you how to read hex, but I will just at least explain that we have numbering systems, and we can have the same number in different systems, right? So in green, you have a number in decimal, and then you have all the ones and zeros that represent that same number in binary, and then you have the boxes that represent the number in hexadecimal with the 0 through 15 0 through F. And so the nice thing about hexadecimal is that with 2 hexadecimal digits, we can represent a byte, which is a really nice sort of convenient way of looking at octets. The most important thing for you to understand is that when you are looking at hex is to not forget you're looking at hex, because otherwise you can have unexpected consequences. So the keys, the format of the keys is defined by a specification called X962, which you'll sometimes see reference to in the names of things. You know, it's always like, I need a key pair, and it's like, well, we have X962 keys, and you're like, is that good? Is that better? I don't know. What is that? You know, and so, yeah. When we're looking at a key, we're looking at something like this, right? Which is basically, it's 2 32-bit numbers representing X and Y, and then that extra parity byte. So we have X, we have Y, and we have that parity byte. And then when we do a compressed format of the public key, then we drop the Y, and then we change the parity byte to either 2 or 3 if it's even or odd. When we're looking at a signature is a very similar thing, because a signature is also 2 32-byte numbers, which we don't call X and Y, we call R and S, but they're encoded in a completely different way, which is called ASN1-DER, which is like the abstract syntax notation 1 distinguished encoding whatever. Rules? Yeah. Anyway, it's just another very fancy specky way of saying this is what you expect when you're looking for 232-byte numbers, which is 64 numbers, the first top of which are R, and the second top of which or second half of which are S. But what you actually get is something that is a little bit, but noticeably bigger. And so if you look at enough of these signatures, what you figure out is that the numbers are there, right? R is there, S is there. It's just that you have these extra numbers here. And so the extra numbers, that's the DER. That's the sort of encoding of what we have here. It's describing basically what these numbers represent. And so you have a sort of section header. 30 is basically like the beginning of the whole thing, and 02 basically means what follows is an integer. And then you have a count behind it, which is the length in terms of the number of bytes that will follow. And so our first, we have 43 bytes total, and then we have an integer with 20 bytes, and then we have another integer with 21 bytes. Of course, that doesn't make any sense because they're 32-byte numbers, and that's because this is hexadecimal, and 20 is 32. Yeah. So how come it's 32 and 33? And the answer to that is because, as it happens, the way that these numbers are stored, sometimes it has to add a padding 0. And when it does have to add a padding 0, then it has to denote the fact that it has one more, which is just, it's a random thing that happens sometimes, which is just sort of like, it's really easy to make a naive implementation of this code to extract R and S without understanding what these numbers actually mean, and then end up running into a problem because indeed sometimes they change. So that's what that means. That's what that is. For the record, Android and iOS both use the same encoding, so you can pass this stuff between them no problem. But a lot of other frameworks, server frameworks, et cetera, all they want is R and S. They don't care about the rest of this stuff, and they're the ones that are going to choke on this. So that's it for the fun crypto math stuff. I hope that you learned something. Or like meta learned something where a year from now you're going to be like, wait a minute, I've heard this before. So now I'm going to spend what little time I have on something that's a little bit more kind of personal, touchy-feely. Just this is my friend Tristan, and Tristan was when I was in Silicon Valley. Tristan was my best friend. He was my right-hand man. He was the first person I hired at my startup, and we worked side by side. He died a couple of weeks ago, and I haven't really been able to process it because I have to work on this presentation. And so instead of like sitting around writing memories of Tristan, I have to sit around talking about cryptography. And so I thought that what would be nice would be to, kind of compromise and just tell a story about Tristan to sort of end this talk. And it's not particularly morose. I just want to remember him for a minute. So this was in 2008. Android didn't exist. The App Store didn't exist. Anybody running an app on their phone was doing it using jailbreak. But the beta SDK was available, and people were just now trying to build stuff on it. At the same time, you had all this money flying around. iFund had been announced, and so it was a really crazy time. We had an election going on in the country. And so one of the apps that we built was an app called Twinkle, and I'm sure none of you remember Twinkle. But Twinkle was the very first Twitter client for iOS. And it had just one really interesting thing about it was that in 2008, Twitter was not the behemoth that it is now. It was mostly just something that nerds were using, but it was starting to get picked up by normals, and so it was starting to have a lot of scaling issues. And everybody loved Twitter, but it was always going down. This was the problem with Twitter, and people were afraid that it was just going to go out of business because they couldn't handle the load. And so people kept making replacements for Twitter, but nobody wanted to leave Twitter because they had already sort of achieved a critical mass, and so people were just kind of stuck. So what we did was we created a Twitter replacement social network that we built on top of Twitter, and then our client, which was a Twitter client, was actually passing the Twitter stuff through our own service so that when Twitter was down, our users would still be able to get messages to each other, and everything else would just be queued. So this was sort of like our genius idea. And this enabled us to put things on top of Twitter services so we could add metadata to the tweets, such as location. Nowadays, we take for granted that tweets have location, but back then it was a brand new idea. And so, we were in Silicon Valley, people were tweeting all the time, and so you could look at your Twinkle and you would see all of the people around you, all of these words being said. It's like you really got this feeling for what was happening in the now, right? Like, what are people thinking right now? So this was 2008, and in addition to working on a bunch of this kind of stuff, we also worked on an app for this presidential candidate that we were all very excited about, named Barack Obama. And so, we worked on the team that made this app for him, which was a huge deal for him to have an app in 2008 when apps were still extremely new, made his opponent look very old. And we also volunteered just on the campaign itself. And so we didn't just work on the app, we also ended up getting in Tristan's car during the election and actually driving across the desert to Las Vegas and volunteering with the campaign in Nevada, going, knocking on doors, canvassing, helping people to vote, that sort of a thing. And so we're driving through the desert, it's the middle of the night, and it's the desert. There's nothing for hours and hours. There's just nothing but us in the car, me and Tristan and his girlfriend at the time, and just the perfect music and the stars. And these ghost tweets from people who had been driving through the desert over the last 3 weeks and tweeted something using Twinkle. And because it was the desert, instead of being something that was only there for a couple of seconds, it was something that had hung around for all this time. And so this technology that for us was something that enabled us to very much have something in the now was suddenly giving this completely different experience of people's lingering thoughts left behind long after they themselves had passed. And it was just this incredibly beautiful, moving moment of experiencing something new together, a way that the world had changed in some tiny, beautiful way, thanks to a piece of technology that we had worked on together. And that's a memory that I'm going to keep with me until it's my turn to be remembered. And I think that for me, really represents what all of this technology stuff has always really been about: changing lives, sharing things together. Thank you.